Okay, this is our second video on the calculus of polar. We're going to do a little bit of area again. And what I'd like to do this time is, again, the area enclosed by both. I've actually gone ahead and color-coded them the way that the calculator has actually color-coded them. So when I actually show you the graphs on the calculator, there will be some consistency there. The blue one is r is equal to 3 plus 3 cosine theta. The red one is going to be 3 minus 3 sine theta. And that should make sense to us because cosine is at its maximum at 1 here at theta is equal to 0, and that'll be 3 plus 3, or 6, which is where it is. It'll be at its minimum over here, and when cosine is 0, you're going to have radii of 3. And same thing sort of holds true for that. Now, I want to find the area between the curves, okay? So I'm looking for this area right here, okay? Let me go ahead and just make sure it's all colored in, okay? Now, but I'm also looking for that little sliver right there. That's going to be the difficult part, okay? So, one thing that I need to remember about these problems is I need to let symmetry help me, okay? So you need to realize that if you can actually do something like that, and you can actually figure out how to find 1/2 of this, then you've cut your work in half, okay? Now, let's try and figure this out. Now, I happen to know that I'm going to have two separate intervals, right? Well, let's go ahead and try to figure out what those are, because actually what the equations are is relatively straightforward. Now, in order to find this, I need to figure out what is going on here, right? I know that this is easy enough to find, and this should be easy enough to find. So if I can figure out where these two meet right here, it should be easy. Well, it should meet down here at 7 pi over 4, or what we can call negative pi over 4. So if we're sort of swinging it around, let's just assume that it's going to go from negative pi over 4 to, well, what's up here? That's going to be pi over 2. Okay? And then maybe, just maybe, we can swing it back over here. So let's assume that if we can actually take this red graph right here, if we can recreate this portion of the curve, okay, by limiting our interval in the calculator, then we may be going someplace, okay? So let's go ahead and let's see. I've gone ahead and blanked out the blue graph, so we have the red graph, okay? Now let's go and let's actually play with the interval. Let's see whether negative pi over 4, okay, that would be 3 pi over 4, 3 pi divided by 4. Let's see whether that actually gives us the right portion of the graph. And it does, okay? So if that gives us the right portion of the graph, we ought to be able to actually just use that as a single interval in order to find both of those pieces and then simply multiply it by 2, okay? And so we're going to go ahead and do that. I basically down here, all I did was just blow up this itty bitty portion right here so we could see it a little bit better. I mean, it's itty bitty, but it is there, okay? I'm going to go ahead and fold this away so we can keep this in view while still doing our analytic work. Okay, so what we need is 2 times the area formula, which is 1/2 from negative pi over 4 to 3 pi over 4 of 3 minus 3 sine theta squared d theta, and that should be it. Okay, and that's pretty straightforward in terms of setting it up. And again, this one would be much like the last one in the previous video. You would just have to multiply this out, FOIL it out. You would have to use power reducing for the quadratic, and it'd be burdensome, but it wouldn't be overly difficult. Okay, so let's go ahead and put this one behind us. Let's move on to sine 3 theta, as I promised. I went ahead and made it 2 sine 3 theta, just so we can get a good look at it. Okay. Now, let's say that I want to find the area of that petal. Okay. Now, when it has an odd coefficient right here, it's a little bit more difficult, because you have to remember that this is actually 6 petals. It's just that the 4th, 5th, and 6th are written on top of the 1st, 2nd, and 3rd. Okay? When there's an even coefficient right here, you can actually see all the petals. When there's an odd, you can't see them because of the way that positives and negative outputs are arranged around the circumference of the polar grid. It winds up reflecting negative petals back on top of positive petals. So in order to get the interval for a single loop right there, what we need to do is we don't need to divide 2 pi by 3, we need to divide 2 pi by 6. Okay? So from here to come all the way back around to here, you're going to start at 0, but when is the next time after sine of 0 that sine has an output of 0? Well, it's going to be at pi. Well, what do I need to plug in here in order to get sine of pi? Well, I need to plug in pi over 3, right? So this first petal is actually formed 0 to pi over 3. Pi over 3 to 2 pi over 3. 2 pi over 3 to pi. Pi to 4 pi over 3. 4 pi over 3 to 5 pi over 3. And then 5 pi over 3 to 2 pi. And that would be 0 to 2 pi. And then we would get, we would basically get the petal that should have been down here is reflected back on top of here and makes that second run around that petal right there. So now we have the interval, and we know that it's 1/2 the interval from 0 to pi over 3, and then we just need to square our r theta, and that would be it. Okay. Well, let's do one that's a little more complicated than that. Let's actually see what happens if we take that same graph, okay, but we want to find the area inside of the petal, and should we go inside or outside the circle? Oh, I don't know. Let's do inside the petal. Okay, so now I'm looking for that area right there. Okay, well, here's the thing. This becomes a little bit complicated because you can actually chop this up a bit, and I'll show you how. You can actually find the first section by evaluating that area right there. You can actually find that last section by evaluating that area right there, but that right there is just the sector of a circle, okay? So it actually stands to reason, and of course those two black areas that I just blacked out, those are symmetrical. So I can actually find this red area right here geometrically as long as I know what theta values are associated with those 2 points right there. Okay, well let's figure that out. Okay, when, and of course this right here is r is equal to 1. When is 2 sine 3 theta equal to 1? Well, that's when sine of 3 theta is equal to 1/2. Well, when is sine equal to 1/2? Wouldn't that be at pi over 3 plus pi n, and at 2 pi over 3 plus pi n? Okay. Well, actually it's pi over 6, sorry. These are wrong. These are wrong. Okay, let's actually move down here since we have a little more room down here. So when is sine of 3 theta equal to 1/2? That's when 3 theta is equal to pi over 6 plus pi n. Okay. And also when 3 theta is equal to 5 pi over 6. Actually, that's 2 pi n. 2 pi n. Okay? And if you can think about it in terms of the unit circle, you can think about it in terms of the sine graph, right? Sine graph does that number, and you're asking when is it 1/2, okay? And that would be at pi over 6 and 5 pi over 6, and not again until the next period, hence the 2 pi n. But you're really not worried about that. You're worried about theta is equal to pi over 18 and 5 pi over 18. So that's a difference of 4 pi over 18, or 2 pi over 9. 2 pi over 9 is your theta. You can find the area of that sector very, very easily just using geometry. The calculus part is finding this black area right here. And so what you're going to need is you're going to need to find that area right there is 2 times, because there are 2 of them and they're symmetrical, 0 to pi over 18 of 2 sine 3 theta squared d theta. And that would be how you would, and then you would just add the area of the sector that you figured out with your, and you actually could use calculus to find the area of the sector. It's just wonderfully underwhelming because the r that you're squaring is a numerical r, right? The radius is not a variable. It's a constant for this circle with its center at the pole, okay? Now, let's go ahead and let's move on to the next order of business in all of this, and that is arc length, okay? Now, arc length, we found the area of one of the sectors of this rose petal. Let's find the arc length, okay? Now, the arc length, and we've seen arc length in Cartesian sort of function form. We've seen it with parametrics. The arc length formula for polar is this, okay? And you're like, well, I know it's got to be a square root and it's got to have derivatives underneath it, and you're right. It goes from a to b, square root of r squared plus, and we'll call it r prime instead of dr d theta, squared, and then just d theta. Okay, so if r is equal to 2 sine 3 theta, and r prime is equal to 6 cosine 3 theta, and I know one of the petals is 0 to pi over 3. I figured that out the first area problem that I did with this 3-petal rose. Then the length is going to be 0 to pi over 3, okay, of 2 sine 3 theta squared plus 6 cosine 3 theta squared d theta. And that's it. And you would basically plot that into your calculator, press enter, and it would pop out a value, and that would actually give you the length of the curve from here around one of the petals. Okay? We'll go ahead and do a little bit more of that in the third video, and we'll move on and I'll show you how to take the equation of a tangent line in polar. And then we'll be done with parametric vectors and polars, and you'll be able to I hope, score well on the test that is coming up. As always, please do email me with any questions that you might have. Bye.